Dark matter. Few words conjure up so much from our imaginations as the word. When we look into the cosmos and see its mysterious gravitational presence in the images of gravitationally lensed galaxies, we wonder what it could possibly be. Is it even anywhere at all? Is it just a farce? Is it even real? Is it just bad data taken by astronomers? So many questions remain, and yet we've already detected one form of dark matter already. The mysterious neutrino, the subatomic particle that plays the pivotal role in nuclear fusion and fission processes. It never emits light, yet we have detected it deep underground, interacting only rarely with nuclei in specialized detectors designed specially to measure these rare but crucial events. And they have been measured, thus confirming dark matter exists. The very life-giving forces of our sun would not exist. The planet would have no energy. We ourselves owe dark matter to our very existence, and yet it travels through us, billions of particles each second, and by some miracle we don't even notice, because the very nature that prevents it from emitting light also makes it incredibly unreactive to the matter in our bodies, thus unharming us. In order to detect this dark matter of neutrinos, we have to travel deep underground and build special devices to detect it with extremely sensitive precision. It took almost 30 years from the time that it was proposed to exist to actually detect it. And yet, we think there's more. We have signs that other forms of dark matter exist in our universe from the beginning. Just moments after the Big Bang, the universe was hot and extremely dense. This was long before Newton's laws. In the early universe, moments after the Big Bang, we didn't have Newton's laws. Instead, we had a set of laws called the Planck scale laws, which governed our early universe. These are the Planck mass, the Planck temperature, the Planck energy, and the Planck time. The Planck energy is formulated in terms of the Planck mass times c squared, making use of Einstein's famous formula of E equals mc squared. In terms of the fundamental constants, we get that it's h bar times c to the fifth, all divided by Newton's gravitational constant to the 1/2, which gives us an incredibly high energy of 1.22 times 10 to the 19 GeV. To put that in perspective, the most energetic processes in particle accelerators can only reach about 10 to the 5th GeV. We also have the Planck time, which is formulated in terms of the Planck length divided by the speed of light, which is h bar times Newton's gravitational constant divided by c to the fifth, all to the 1/2. We get that it's 5.39 times 10 to the minus 44 second. And finally, we have the Planck length, which is only 1.62 times 10 to the minus 33. 10 to the minus 33 centimeters is an incredibly short distance. Now you can see these quantum fluctuations occurring. Just think of it as happening in such a small volume like this. And at the same time, there's particles of matter and antimatter popping into and out of existence. And these particles exist for only a fraction of time, the Planck time, something like less than a trillionth of a nanosecond. And at the same time that there's particles of matter and antimatter, some of that we think is dark matter. So there's dark matter and anti-dark matter popping into and out of existence as well. And the universe is also expanding while this is happening. And that's really what starts to change, because as the universe expands, it starts taking longer and longer for these particles of matter and antimatter to meet and annihilate. And that's when we start to see a big change happen. The big change happened for the universe when the photons, which were the radiation, decoupled from the plasma, meaning that the photons no longer got trapped in this hot soup, but there was enough volume for the photons to be able to travel freely, and they were no longer bound to this hot plasma. This is a time in the universe when things began to cool remarkably fast, and this is known as the photon decoupling event. We can still observe this decoupling today. The evidence for it is the cosmic microwave background radiation. The CMB is observable as radiation at a certain microwave wavelength in every single direction that we look in the universe. This increase in volume for the universe also affected other particles. For example, if dark matter is its own particle and antiparticle, then during the hot early universe, its abundance would stay constant, as shown here in the plot, because there's an equal number of particles being created and annihilated simultaneously. However, as the temperature of the universe goes down, we suddenly have this purple epoch here, where the dark matter particles are meeting and annihilating and decreasing, but there's no longer enough heat and energy at any particular point to create new particles, so we actually have a decrease. At a certain point, though, the particles can no longer meet and annihilate because the density isn't high enough, so then we have a constant value, which gives us the blue epoch, when all the particles and their abundances stay constant. Now we have a situation where the co-moving density is constant. When this happens precisely depends on the cross-section. Later means a larger cross-section. So this gives us a way to relate the macroscopic observable property, which is the current energy density of dark matter in the universe right now, to the microscopic property, which is the cross-section where this happened. Meanwhile, the universe is still expanding, but the particles that have formed are starting to gravitationally attract. So we have a dual situation. On the one hand, the universe is getting bigger because of dark energy and the expansion from the Big Bang. In fact, this expansion is even accelerated, so the universe is growing larger by the second. But at the same time, the particles are now stable, and gravitational forces are starting to take over. The universe is starting to look more classical in its laws. Here you can see this formation of small galaxies. These first galaxies would be really nothing more than cold clumps of dark matter and hydrogen. We're still at the stage where the first stars have not yet formed, yet we can already see the structures where there's voids of empty space, and then regions of high density where there's matter that will ultimately become the seeds of our first galaxies. The dark matter potential pulls in the gas and traps it. Remember, dark matter represents about 75% of the known matter in our universe. So this dark matter is going to actually be the glue that holds together these gas clouds and causes them to gravitationally form into the product of galaxies. Now, interestingly enough, there's actually a lot that we can learn by how big galaxies are. Because if the dark matter particles that form the majority of our universe and our galaxies were fast moving, like, say, neutrinos, which are dark matter that travel almost at the speed of light, well, then we wouldn't have all of these types of gravitationally bound structures forming, because the dark matter would have too much kinetic energy to be gravitationally attracted to any meaningful size. So the fact that we have these large structures and these galaxies forming even in an early time in the universe points to an identity for a dark matter particle that is massive and also slow moving, hence the term cold dark matter, as opposed to hot dark matter, which would be a fast moving form of dark matter, like a neutrino. When we look at simulations of galaxies such as these, we see that without dark matter, we don't have the kind of large-scale structure formation that we actually observe. In fact, the dark matter is needed because it slows down the particles and allows them to form into galaxies. So we now have a new picture of the role that dark matter plays in galactic anatomy. Essentially, dark matter and its gravitational potentials that are associated with it are like the skeleton holding everything together. They gravitationally attract gas, and in turn, this gas is pulled together and slowly cools and forms the first stars. Without the process of the dark matter bringing it together, we simply wouldn't have the formation of the first galaxies. And again, we need these stars to form so that they can in turn die and produce the first black holes that become the center of our galaxies today. We think that the majority of supermassive black holes formed in these early stages of the universe as well. When we look at the early origins of our own Milky Way, it probably looked something like this: a collection of closely packed yet giant stars, which supernovaed, some of which turned into black holes. The black holes then merged together to form a supermassive black hole, which formed the central potential that would become the Milky Way. Then smaller galaxies were attracted to this centralized potential, and they were pulled apart and incorporated into a larger galaxy. This process probably repeated itself many times over and over again over the course of the development and led to the Milky Way as we see it today. But where does dark matter come into this picture? I mean, we have this image of stars forming the first galaxies, and through their deaths, they produce these supermassive black holes, which in turn attract more matter and sort of create this centralized, almost pseudo-Keplerian potential where we have a very dense region, and all of the stars and everything else in the galaxy orbits it. That's the Milky Way today. But there's also a region of the Milky Way, the outer halo, that extends 300 kiloparsecs. So for perspective, we're nowhere close to the center of our galaxy. We're about 8.3 kpc from the center of the Milky Way. But we have a halo of dark matter, so to speak, that extends about 300 kiloparsecs away from us in every direction. This could be the Milky Way. Here we have all the stars and gas forming the spiral structure and the supermassive black hole at the very center, Sagittarius A star. But notice, well outside of this, we have this diffuse sort of ghostly looking halo surrounding everything. That's the dark matter. And if our modern perception of dark matter is correct, and dark matter is a particle, then it was there all along, and it essentially helped bring everything together. But it didn't really do much, because remember, these particles had been frozen out at a very high energy. They were created at a moment when the universe was much hotter and denser. So it takes a lot of energy to disrupt these particles and make them do anything. They're very inert, and they don't really interact very much with anything else. Or do they? Enter the Fermi-Lot telescope, a special gamma ray telescope that can look at extremely high energy photons. Gamma rays are well outside the visible range of radiation. They have way more energy than even an X-ray. But they're very important to physics because they indicate high energy processes. Whenever you have a situation where there's a particle physics collision, say two particles colliding with each other, then a lot of times you'll have these gamma rays produced. If it's something like an electron and a positron, for example, so a matter-antimatter pair. When Fermi-Lot launched, they began looking at the galactic center of the Milky Way to see if there was anything there. What they found was amazing. There was an excess of gamma rays. And by excess, I mean there was extra gamma rays that they saw at the center of the Milky Way and near the center that could not be attributed to any normal sources such as heated gas. They have been potentially attributed to millisecond pulsars and other forms of high energy stars or processes that occur, such as supernovas. However, this is still under debate. One possible source of the gamma rays might be dark matter. Here's the image of the galaxy taken by Fermilot. There's an excess of gamma rays in the picture. The source of these gamma rays is widely debated. Many think that the gamma rays are simply produced by pulsars, neutron stars that are rotating rapidly and producing the gamma rays as a form of synchrotron radiation. Others think that the gamma rays are produced by other sources that are not dark matter. However, we haven't ruled out the possibility that dark matter might actually be meeting with its antiparticle and annihilating. Another possibility is dark matter might be interacting in some other high-energy way. The important point is there isn't a lot of processes that produce these gamma rays, so narrowing down the source is feasible and possible. I'm going to explain how we're doing that next. But first, I want to talk a little bit more about the research that we've been doing with galaxy simulations. We construct these high-resolution galaxy simulations, and they have different particle types. We start out with a bunch of gas in the early universe, and dark matter as well. The gas forms into stars, and then the stars in turn can supernova and produce black holes, or if they're small enough mass, they go on living for a very long time, because low-mass stars essentially live for billions of years longer than high-mass stars. In these simulations, we then study how the galaxies form. I then look at the galaxy at the lowest redshift possible, which means the most recent time, essentially the time that our universe is at right now. And I look at galaxies like the Milky Way to see what their galactic centers look like. Here's an example of one type of galaxy that I've been looking at. This simulation was done using Fire 2. It was run by a team including Andrew Wetzel and Phil Hopkins, using code that essentially creates galaxies through a numerical simulation. This is the galactic center. Here I've zeroed in on a radial area from 0 to 30 kiloparsecs. In this region, known as the galactic center, we are looking for what dark matter potential exists. As you can see, even for this galaxy, the majority of the dark matter is located at the center. There are some substructures, meaning some regions of higher density at other places too. You can see those as well in this image. There's dots here and there. But the majority of it is in this galactic center. And a lot of the work that I'm doing that follows focuses in on this inner region here of the galactic center. So the first thing that we wanted to do was we wanted to look at the density of dark matter as a function of radius. And you can see it here. This is unnormalized density profiles. They peak at right around 10 to the 9 solar masses per kiloparsec for the largest galaxies. And the blue ones represent the fire galaxies that had gas and stars in them as well. We can also make dark matter only simulations, which are the black dashed lines. Now, both simulations are majority dark matter, but there's a lot of differences in the simulations when we include the effects from stars and gas. And the effects are more visible when I look at the normalized density profile. What do I mean by a normalized density profile? I normalized each density profile so that it has the density that we measure for dark matter in our own Milky Way. The next thing we wanted to look at was what's the velocity dispersion for these particles in these galaxies. Here we have curves representing the different velocity dispersions. And as you can see, they go really high as 600 kilometers per second in some cases. The interesting thing is the fire simulations that had gas and stars as well as dark matter, the galactic center, that's this inner region of from 0 to 10 kpc, those had the highest enhancement, meaning the particles were going really, really fast in these inner regions, much faster than in the dark matter only. This is relevant because if the particle collisions
involve higher kinetic energies. It could mean that annihilation and production of gamma rays, therefore, is more probable in these types of simulations. And they might be more probable in real life too, because obviously in the Milky Way we do have gas and stars. Now, why do we care about velocity dispersion and density of dark matter anyway? Because we're interested in measuring the potential production of gamma rays from particle physics collisions. These sets of equations, which I'm not going to go into great detail here, describe that. But the key takeaway is there's three main types of collisions that we're interested in. S-wave, where the number of gamma rays produced depends directly on the density along the line of sight squared. That's because we're not looking at velocity dependence. We're just looking at the probability of two dark matter particles meeting, and that's directly proportional to the density squared. P-wave, where not only is it proportional to the density squared, but it's also proportional to the velocity squared, the velocity difference that is between one particle and the next. D-wave, where it depends on velocity to the fourth and the density along the line of sight.
Now, what do I mean by density along the line of sight? Well, here's another sort of schematic representation of what I'm doing here. So this is the equation that really tells us the flux of particles we can expect if dark matter interacts in some way. There's a particle physics piece, which isn't really a factor. That just becomes some sort of constant value. We could sort of think of it as not really depending upon the astrophysics of the situation. Now, the astrophysics has to deal with geometry and the orientation of the galaxy. Because if I'm looking at a galactic center, I'm looking at it with a telescope. And what am I going to see? I'm going to see photons. But the photons that I'm going to see are only going to be coming from particles that are interacting along the line of sight of my telescope. And it doesn't matter whether it's an optical telescope or even our eyes, or in this case, a gamma ray telescope. Regardless, it's only going to depend on the line of sight. So in order to do this calculation correctly and accurately model with a galaxy simulation what I would actually see in a real galaxy, I have to take that integral along the line of sight. That's a tricky calculation, and I won't go into the details of it here, but that's been done. Another really important thing that I needed to do to get this analysis correct is I had to position myself 8.3 kpc away from the galactic center, because that's how far we are from the center of the Milky Way, and any telescopes that we launch is essentially where we're at, about 8.3 kpc away, give or take a million miles or so for some of the telescopes that are space telescopes. And I use this coordinate transformation to place myself there. Then I do a spherical polar coordinate transformation because it's easier to do all the rest of the analysis in that coordinate system.
And here are the results from doing that integral for all of these different positions. I'm pointing my telescope in the sky and calculating the J factor. And I have three different results. On the top, we have S wave for dark matter only, which is on the left-hand side here, and fire, which is on the right-hand side. Then for P wave, dark matter only, the results are here, and for fire, they're here. And then finally, for D wave, dark matter only here, and fire on this side. What these results show is they show that there's an enhancement when we look at the full baryonic physics, meaning that it increases the density, it increases the velocity dispersion, so it increases the probability that we have these potential gamma rays produced. So we should be able to measure these, especially for the case of P wave.
But what do I mean by enhancement specifically? Here I have the sky maps, which essentially is a measure of the predicted gamma ray emission that we could expect to see. Notice that I have a name in the left-hand corner, Juliet. That name is the name of this particular galaxy. You see, this simulation not only included one galaxy, it actually included two. I looked at one set of galaxy simulations that just had a single Milky Way type galaxy in it, but I looked at another set that had a Milky Way and an Andromeda pair. This comes from the simulations that had the pair. Juliet represents the Milky Way. Its pair, Romeo, represents the slightly larger Andromeda galaxy. Now, there's important results that I need to illustrate here. This is for S-wave, so this only depends on the density along the line of sight. There's no velocity dispersion. But notice how different these two maps look. Why do they look so different? Here's why. The map on the left is a galaxy that's only dark matter. There's no other particles interacting when this simulation runs. We have all of this substructure, and what happens is the substructures form naturally due to gravitational interactions with the dark matter particles with each other. But if I have baryonic effects, meaning that I have stars and gas in the simulation like I do on the right, these substructures get suppressed, and I have a more larger centralized bunch of dark matter, and all of these smaller galaxies sort of get suppressed due to the energetic feedback mechanisms. Basically, the gas and the stars heat everything up with supernova events, and these energetic feedback mechanisms due to stars supernovaing heat up the dark matter and prevent them from gravitationally forming at certain sizes. In other words, the particles are moving too fast to form into galaxies unless there's a really large number of them. It's kind of like in the early universe when we had stars forming. The stars were much more massive because hydrogen and helium were the only gases in the early universe. So they had to form much larger. Otherwise, they would just escape the gravitational potential if there wasn't that much mass there. Same idea here. Ultimately, what happens is when we have these baryonic effects, we actually have a larger potential of dark matter in the center, something called baryonic contraction, because all of that star and gas material that forms the galactic center, it attracts the dark matter in these simulations. And the question is, how accurate is this picture of dark matter? Do we actually have dark matter at the center of the Milky Way galaxy? That's a really important question that my research is looking at as well. And we actually have measured the black hole, the supermassive black hole, Sagittarius A star, and we have a mass reading for that. The issue is, it's such a small volume of space, actually, because we're really looking at the inner kiloparsec of the Milky Way. It's such a small region that we just don't have delicate enough measurements yet for the dark matter to say if there's any dark matter there or not. Obviously, if there's dark matter there and it follows the results in our simulations, that's great. But it's possible that the dark matter does not follow the distribution that we see in our simulations. And we need to figure this out because this is a really, really important mystery. If the dark matter is not distributing itself in this centralized peak where we have the majority of it, the greatest density, I should say, because it's not the majority of the dark matter, it's a small volume of space actually, but we have the peak of the dark matter at the center of the galaxy in these simulations, and then it falls off, but it falls off more slowly than the stars and the gas, so the majority of the mass in our galaxy is still dark matter in our simulations. The question is, does the Milky Way actually look like this? For the time being, we don't have an answer. So we're just going to have to work with the simulation as it exists. And it's pretty consistent with other simulations and what we see. So we'll just go with it for now as a rough approximation. Let's say that this is a rough approximation of the dark matter density. This map then represents the density squared along the line of sight, which then produces the gamma rays. And the J factor is the actual thing that we're looking at here. You can see this scale here that goes up to 24. That's log 24. So that's 10 to the 24. The units are giga electron volts squared per centimeter to the minus fifth. It's basically your density squared per steradian. You could think of it as like how much density along my line of sight I have. But the units are not quite energy. They're not quite a normal unit like you'd think of for like energy or something like that. They're sort of these geometrical units where when we combine that with the particle physics piece, we actually get an energy then. So basically, you can think of it as it's a measure of how many dark matter particles we'd expect to see producing gamma rays. So ultimately, the units come from the density, which is mass per unit volume, times the line of sight. So it's actually giga electron volts squared per centimeter to the minus sixth because we have a volume squared as well. However, we also have a density along the line of sight, which takes away one of those centimeters. So that's why it's centimeters to the minus fifth. And then all of that per unit solid angle, so per steradian. Next, I have the same information, except now it's put in a plot. And this shows us the shape of the emission signal. So what I just showed you a second ago was the emission signal of gamma rays in terms of the J factor. Now I'm showing you how does this emission signal go in terms of angle. So as I go further out with angle, you can see it drops down. Now, this is for S wave, so we still haven't gotten any velocity dependence yet. This S wave annihilation would mean that two dark matter particles, a dark matter particle and an anti-dark matter particle, for example, get brought into close enough contact through gravitational interactions, being with the density being higher in the galactic center, and then they annihilate. Now, is there anything in nature that works that way? Yes. If we have a density of, for example, electrons and positrons, if we have some source that's producing positrons and another source that's producing electrons, and we have densities of these two particles in some region, they're going to annihilate whether they're going a certain velocity or not. So if dark matter works similarly to leptons like electrons and positrons, then we would expect to see a signal that looks like that. It's also possible that dark matter does not work that way. There are situations in particle physics when an interaction and a collision is velocity dependent. So I'm going to talk about that next. But for the time being, just know that that's what we're talking about here when we have these kinds of plots. We're talking about the energy and the likely signal that we are going to see if we have some kind of interaction based on density of dark matter. Now, what happens when we include velocity dependence in the equations? Well, we get some interesting changes. Our signal actually gets smaller in magnitude. That's because for every power of velocity, we have to include a factor of c associated with it. And that's because essentially we're converting to units of energy. And so by the E equals mc squared, we have to convert mass into energy by dividing by c squared. The same idea goes into play here. So we actually get a smaller value of a detection signal. Now, when I say a smaller value, that's relative to the background signal that we're going to be getting. So it doesn't necessarily mean a smaller energy, so to speak. The main thing that is of major interest to us here is the enhancement that occurs with velocity. You see, when we look at the emission signal predicted on the right-hand side for fire, we see that it's much larger in the galactic center than it is for the dark matter only runs on the left. This is because we find that in the galactic center, the velocities of the dark matter particles are vastly heated up by interactions with the stars and the gas. And so these particles are going much faster. So if an interaction depends on the relative velocities of the dark matter particles, we're going to have way more interactions in these fire runs that include gas and stars than we are in the dark matter only. This is important because prior to this analysis, other groups had looked at J factors in dark matter only type simulations, and they hadn't looked at things at this high of resolution. The simulations that we used are much higher resolution than the standard runs and the standard galaxy simulations like Illustris. Fire has that advantage going for it. So that's one of the things that really strengthens this work, is that we have these really high resolution results showing what exactly we would expect the signal to be like for this kind of a potential dark matter interaction if it depends on velocity. And then finally, I want to talk a little bit about D wave. So D wave is a type of annihilation that's particularly sensitive to velocity. It actually goes to v to the fourth power. And because of this, we actually have a further suppression on the actual signal magnitude. So if you notice here, you see this log scale, it only goes to like 11.5. And the reason for that is because every time we add a value of velocity, we have to divide by a power of c. Because remember, we're in the units where we're converting our masses into energy. E equals mc squared. So we want to be in these consistent units. So we're having a factor of c that's lowering our overall signal magnitude. And this is important because what I'm going to do next really ties everything in to what I've been building to up to this point. So far, we've just looked at these hypothetical signals that we would expect to see from galaxies if we had dark matter. But how does that relate to what we actually observe with a telescope? This is where I'm going to bring that all back together. And it's going to tie back in with the very origins of dark matter at the beginning of the universe. Recall our original discussion that I had where I talked about in the early universe we had dark matter particles creating and annihilating in equal abundances because we had this hot plasma soup in the early universe, and we just have all of this matter and antimatter continually creating and annihilating, including dark matter. But eventually, because of the expansion, the dark matter particles are no longer created because the underlying space isn't hot enough. You could think of it like if you have particle collisions today in a particle accelerator, you need an incredible amount of energy density to create a Higgs boson. But back in the early days, the Higgs bosons were just everywhere. But nowadays, they can only exist for a tiny amount, and then they disappear. Their number abundance goes down because we can't maintain that energy density because the universe is too big. Same idea here. Basically, the dark matter particles number abundance is just decreasing because they're meeting and annihilating, and they're no longer being created out of the vacuum. It's not hot enough anymore. But eventually, they can no longer meet and annihilate even. So in the blue epoch, they stay constant. And notice when I say increasing here, what I'm talking about is there's a cross section. And basically, there's 3 lines there. And what those are is, those are different values of co-moving number density. And the point at which that equilibrium point happens changes this cross section. So if I have an S wave or a P wave or a D wave type of interaction, I'm going to have different energies associated with that and different cross sections associated with that. So if I actually detect one of these forms of interactions, I'm going to know where to look for my cross section for my actual observational signal. Because the cross section, that term in the brackets, that sigma AV, that's what we're really trying to measure with a telescope. We're trying to look at the data and say, hey, do I see a cross section for an interaction? Is there dark matter particles that are interacting and producing gamma rays associated with that energy of what I think the mass of this dark matter particle could be? The more massive it is, the faster it froze out. Because remember, if the Higgs boson is really, really heavy, you need a tremendous amount of energy to make it. So the heavier the particle is, the faster it freezes out. If it's lighter, it's going to freeze out at a later time. So we have this situation where we actually observe how much dark matter exists today in the universe and at what energy does it exist. In other words, what are the energy of my photons produced when dark matter meets anti-dark matter? And those energies are going to tell us its mass and when it froze out. And so that's really what I'm trying to look for with my Fermi-Lot telescope. And what we find with our data is interesting. We find that we could actually measure this with the next generation of telescopes because we're going to have better telescopes coming online soon measuring these gamma rays. And we can determine potentially if there's an interaction occurring. I want to emphasize that the Higgs boson is not a form of dark matter. I'm only bringing up the Higgs boson as an illustrative example of a known particle that we've measured because all of the dynamics of the amount of energy we need to produce a particle, it's all quantum field theory. And whether it's a Higgs boson or a dark matter particle, the same fundamental quantum field dynamics should apply. And so really it's a way to show that a heavy particle would freeze out at an earlier time because a heavy particle would require a higher energy density. Now that's relevant because we have evidence that these particles, these dark matter particles, are massive. In fact, that's where the acronym WIMP comes from. It stands for a weakly interacting massive particle. We think that most of this dark matter that we see in galaxies is slow moving. It's not going really fast like a neutrino. Therefore, it's probably got a lot more mass to it. Neutrinos have very little mass. They do have some, but it's almost zero. Actually, we don't know exactly because measuring the mass is difficult, but we think it doesn't have much mass. The WIMP, on the other hand, we think probably has a lot of mass. So its high mass means that it probably froze out earlier. But we'll know for sure if we can pinpoint a specific gamma ray energy in the data that could correspond to this cross section that we see here. What you're looking at in this plot is a cross section as a function of mass. As you can see, there's a line required for the thermal abundance that we observe. If it's S wave, it has to be above that line. Anything that's below it is ruled out. As you can see, it better be almost 10 to the 3 GeV in terms of its mass if it's S wave. Otherwise, it's been ruled out in this analysis. I basically compared my results to another group, Abazagian et al., and another paper where they did the analysis, but they only did the analysis for S wave. I actually went on further and did the analysis with my advisor James Bullock for P and D wave, and we together looked to see how would this signal be affected if we did have velocity dependence. For now, you can just look at this plot and say, okay, if it's a WIMP and it annihilates through S wave, meaning it only depends on the density and not the velocity, it would have to be a massive particle, and it would be very difficult to detect because it's very hard to detect energies like that and rule them out from other sources. So this would be a difficult observational result to compare to, but maybe not impossible. It also means that a very large swath of WIMP masses are not viable that have been predicted from theory for S wave. But again, it's not impossible. It we haven't detected particles that are generally in this mass regime before, but that doesn't mean that fundamental particles like this couldn't exist. It's not beyond the realm of possibility. However, let's see what these results look like for P wave and D wave. For P wave, we have a very different cross-section range. As you can see, we're much higher up, and we now have a situation where the abundance required from the thermal abundance model is way down. That means nothing is ruled out under P wave. And interestingly, this range of 10 to the minus 22 to 10 to the minus 21, that's within the range of detection for modern telescopes. So we have a chance of maybe detecting this soon. Look how close it is to this thermal abundance required. That's one of the reasons why it's so possible that it could potentially be detected within the next couple of years as our telescopes get better. Now, the constraints that we got, we actually found these from our simulations. So that's what you see here when you see these blue lines. These blue lines represent the results for 12 different simulations. On the left, we have the dark matter only results, and on the right, we have the full fire physics. The fire physics is even closer to the thermal abundance, which is great because now we have something that we should be able to measure with a telescope if it exists. So this is a very predictable result, something that we can actually measure with an instrument with a telescope to confirm. It's not something that we can't measure at all. And lastly, we have the situation for D wave. Now, D wave, the requirement for thermal abundance is way below what the values would be based off of our constraints. So this means that if dark matter behaves like D wave, it would be more difficult to detect it because there's so many orders of magnitude between where the thermal abundance is and where these energies are falling. I wouldn't say that it's impossible, but it would be much more challenging. So the bad news is that D wave is not in that sweet spot for a detection with a telescope. However, I would say that P wave is more likely to be the type of interaction favored by nature if velocity dependent interactions are the one favored for dark matter particles interacting. The reason for this is pretty simple. When we have collisions and things that occur on a classical scale at low velocities, we can typically get a pretty good approximation by looking at the first order situation with our equations. We don't have to look at any relativistic effects when we're at lower velocities. And the cross sections don't do anything funny with geometry. We don't have to worry about length contractions contributing a significant role to our interactions. And the way we do when we're colliding protons that are going close to the speed of light. And we think that the dark matter is traveling very slowly because, again, if it was traveling fast, it wouldn't be forming or serving as gravitational potentials for our galaxies even now. It would be flying around everywhere with a bunch of kinetic energy, and we really wouldn't even have galactic structure. You can't produce stable galactic structure from particles that are moving really, really fast. It just isn't possible. We need, if these dark matter particles are in fact there, they should probably be very slow moving because, again, gravity is winning. It's dominating over these, kinetic energies. And if it wasn't, we still wouldn't have gravity forming into galaxies even today. So that's the reasoning behind why this velocity dependence is probably something simple like v squared, like we'd see with p wave. But again, nothing is certain. We'll have to really look carefully in the next coming years with our telescopes to really get a good sense of where we stand. But it's very encouraging that from simulations alone, we've been able to get some insight into looking for the mass range of a potential WIMP interaction for indirect dark matter detection. And this shows you the importance of simulations and the importance of these calculations looking at all these different factors. For example, with the fire physics, we found that we had a much different structure in the galactic center, a lot more matter and clumping going on in that central area than if we had dark matter only. But we, of course, know the universe isn't dark matter only. The universe has to have this baryonic component. So that's the model that we're working with. And this model gives us a really nice way to test our theory, because we can look with our telescopes and we can look for emission signals and compare how do these emission signals that Fermilot and other gamma ray telescopes are detecting compare to what our simulations are telling us. I showed just one way that I'm doing this now, looking at the overall magnitude of the signal and looking for a probable cross section. But actually, there's other ways that we can do this as well, which I'll talk about in future videos, which involve actually looking at the shape of the dark matter emission signal and comparing it to the shape that we actually observe. Thank you for watching this video. Before I conclude, I'd like to mention that I have a paper out, and this goes over a lot of the things that I talked about, but in a much more detail. I'm also working on a book that discusses this and also gives coding examples for how you can get started in basic simulations and analysis. So I encourage everyone to post lots of comments and questions in the dialogue here and in the chat windows, because I do listen and read the comments and I try to provide helpful feedback. Thanks again for listening, and the paper is freely available on the archive link, and I will put the links to where you can read my paper in the description. Thanks again and have a great one.